Hello everyone, welcome to another video of Naukri learning. So in this tutorial, we will look at what are Naive Bayes classifiers in machine learning and how to implement them in Python. First, we will understand their basic theories, type of Naive Bayes algorithms, and how to use them. And then we will see hands-on application on few of the datasets. So before proceeding, let us set up our tools and the IDs that we will be using for this exercise. So right now I'm using VS Code. It is a very good ID and it has supports for almost every language, and it can also support Jupyter kernels and Jupyter notebooks. So if you have Python installed in your system, you can just create a notebook and connect your Python with that. So as a rule of thumb, for any project, we should create a virtual environment. So for this as well, you can go ahead in your terminal and type Python 3 -m v and give a virtual environment's name, whatever you want to call it. I want to call it v1. So once you hit enter, a new virtual environment will be created, and then once you go inside bin, you can copy the path for the activate file, and then you can run source command to activate that. So right now I already have one virtual environment already created in my PC. So I will just go along and use that for now. So once you have your project set up and your virtual environment created, you can go ahead and add a new file, random f1, and you can give the extension of ipynb. Okay. So once you open this, if you do not have your IPython kernel package installed in your virtual environment, it will suggest you to install that. And once you go ahead and install that, you will be able to write Python codes over here. Okay, so this is a Jupyter notebook interface inside VS Code itself. So you do not need to go ahead and download Anaconda distribution in order to use Jupyter in your local system anymore. So now that we have set up our project, created a virtual environment, and know how to create a ipynb file in VS Code, we will go ahead and learn the theories of Naive Bayes algorithm, and then follow along with the different types of Naive Bayes, and then go ahead on hands-on examples. So Naive Bayes algorithms are a group of classification algorithms which are based on Bayes theorem. So if you are familiar with high school probability, then you might have heard about Bayes theorem as well. So Bayes theorem states that probability of an event C happening given that X has already happened is equal to probability of X given that C has already happened into the probability of C happening divided by the probability of X happening. So to understand this, let us take a dataset and interpret this equation. Okay, so we'll take this particular dataset where the first column state the country of a particular individual, whether they were an existing iPhone or not, and the final column states that whether they have bought a new iPhone 14. For our first example, let us consider only these two columns, the country and whether they bought an iPhone 14 or not. So in this problem, we want to figure out the probability of a citizen who is of USA and the chances of them buying an iPhone 14. Once we put this to an equation, this is how we can interpret this equation. Probability of buying an iPhone given that they are a citizen of USA is equal to the probability of being a citizen of USA given that they have bought an iPhone 14 into probability of buying an iPhone 14 divided by probability of being a citizen of USA. So suppose this particular probability comes out to be, so let me write this down. So say the probability of buying an iPhone given that they are from USA comes out to be 1/4. Similarly, probability of not buying an iPhone given that they are from USA comes out to be 2/4. So whichever probability is higher, that is the probability that we can expect from a citizen of USA. So suppose right now this boils down to 0.25. This boils down to 0.5. So we know that this is the probability that is higher. So next time we see a US guy, we can say that the chances of him not buying an iPhone is more than his chances of buying an iPhone. Okay, that is how this equation is interpreted. So for each class value of this particular category or the target value, we figure out the probability given a feature, and whichever probability comes out to be maximum, that is the target that we are able to expect from that particular feature. So another point to note over here is, since both the denominators are of same value, we can actually eliminate them in order while figuring out which one is greater. So say I have two variables, one is a, which is 1 by 4, and another is b, which is 2 by 4. So in order for me to figure out whether a is greater than b or not, I actually do not need the denominators which are of same value. I can still figure out that even if I remove this denominator, which is 4, my result will always be b is greater than a. So in order to save the computation, we just remove the denominators, since it is going to be same for all the classes across the target variable. So now that we have looked a one feature to a label correspondence, let us see how we can include more features in our dataset and still be able to predict. Okay. So for that, Naive Bayes algorithm makes two assumptions. First is all the features from in your dataset are an equal contributor. So we do not assign any weight to country, or we do not assign any weight to whether they were existing iPhone user or not. Okay. So this way, both of them are equally contributing to whether they bought an iPhone 14 or not. Okay. The next thing is, all the features that we are going to use from our dataset are independent of each other. So there is no way that an existing iPhone user is influenced by his nationality. Okay. So in another way, we are not saying that there is any correlation between being from USA and being an existing iPhone user. Okay. So once this relation or these assumptions are made, actually our probability boils down to this particular equation. How? So if you have taken probability classes, you might know that probability of A given B, when both A and B are independent of each other, is probability of A into probability of B. So to interpret this particular equation, we can say that probability of buying an iPhone, given that they are a citizen of USA and given that they are existing iPhone user, is equal to the probability of them being an US citizen and having bought an iPhone 14 into probability of them being an existing iPhone user and having bought an iPhone 14. And it could be n number of features which are multiplied again by whether they have bought an iPhone or not. So once this particular equation is established, for all the cases, we will figure out the probability. So we will figure out the probability of buying an iPhone when they were citizen of this particular country and they were existing user or not. That will be one of my probability. The other one would be probability of not buying an iPhone given all these conditions. Whichever comes out to be the maximum, that is going to be the probability or the prediction from our side whenever we see a similar kind of feature. So there is also one term called argmax. Okay, so it states, so we will be using only that particular class which the probability of which has the highest value given these particular set of features are used. In this case, we just have two classes, whether they bought an iPhone or not. So whichever probability of from these two classes given a set of features is matched, that particular class will be the predicted value for our case whenever we see similar features from the input side. So this gives a basic idea or the intuition behind how Naive Bayes algorithm works on probability. These algorithms are later tweaked or modified a little bit to work specifically on some kind of datasets. Okay, so we are going to look into the type of Naive Bayes algorithms and when to use which one. First type that we are going to see is Gaussian Naive Bayes algorithm. In Gaussian Naive Bayes algorithm, it only takes features which are continuous in values and which follows Gaussian normal distribution. So if you plot these particular set of features, so in this table we have age, salary, and then another class which states whether they bought iPhone 14 or not as 1 and 0. So we see that age and salary are continuous variables, of course, and if we plot them in their distribution or KDE chart, we will be seeing a bell curve, okay, or a normal distribution. So if we see such kind of trends in our datasets where we have all the features in our continuous form and they follow Gaussian normal distribution, then we can go ahead and use Gaussian Naive Bayes algorithm. So this is a sample dataset that can be used for Gaussian Naive Bayes algorithm, or similar datasets to this particular one can be used. The next one is Bernoulli's Naive Bayes algorithm. So in Bernoulli's Naive Bayes algorithm, it takes features which are only having two classes. Okay, it could be binary class or it could be just two classes in general. So you can have gender, which is male and female, or you can have just Boolean classes. So whether they speak English could be a Boolean class, or whether they speak French could be a Boolean class. And then you have your target variable, which could be a country or anything, which can be of multi-classes as well. So this is a sample dataset where all the features that we are going to use, say speak English, speak Hindi, speak French, speak Spanish, are of Boolean type, and the target could be of multi-class. Then moving forward, we have multinomial Naive Bayes algorithm. So in this particular algorithm, this is more tweaked towards NLP processing, and wherever there is frequency included with one particular feature. So just to give you an example, take this dataset where we have rows which define, say, a movie name, and then star rating. Okay, so how many star rating did it receive in 1 star? How many ratings were there which had given it 2 star, similarly till 5 star, and the type of movie, whether it was hit, super hit, or flop. Okay, so in order to determine whether a movie was hit, super hit, or flop, we actually need to look at all the count of star ratings that it has received across various categories. So we need to know how many 1-star rating it had received, how many 5-star ratings, how many 4-star rating it has received, in order to decide which category the film falls in. So in such cases where the count of the feature or the frequency of feature is also important, we can use multinomial Naive Bayes algorithm. It is also used in NLP processing in order to determine the language, or in spam detections as well, where the count of word is also important. So the next thing is complement Naive Bayes algorithm. So this works similarly to multinomial Naive Bayes algorithms only, but it works magically when there is imbalance in the dataset. So right now, see, multinomial Naive Bayes takes out the probability of a film being super hit when these conditions satisfy. But in real life scenario, we might not have that many instances which can prove this conclusion. There could be other classes as well which are dominating in number to this particular instance, and thus we have a skewed probability. So in order to avoid that, if there is imbalance in the dataset, we can use complement Naive Bayes algorithm. So how it works is it takes the complement of being in a particular class. Okay, so if you want to find whether a particular movie is super hit or not, it will actually find whether a particular movie is not super hit. And if that probability comes at low, then it will state that yes, it is a super hit movie. So similar kind of dataset which we can use in multinomial Naive Bayes algorithms can be solved via complement Naive Bayes algorithms itself. But the catch here is that if there is imbalance in the dataset, the complement Naive Bayes algorithm will perform better. The next thing that we're going to look at is categorical Naive Bayes algorithm. So in categorical Naive Bayes algorithm, it's kind of just opposite to Gaussian Naive Bayes algorithm. It says that all my features need to be categorical variables. Say for this particular example, we are taking skin color and language spoken, which both are categorical variable, and then we can predict their country. So this actually rolls about the theories of Naive Bayes algorithms. Next, we will look into how to solve each kind of problems, and we will solve them using Python. So now that we have a basic idea about the theory of Naive Bayes algorithms, we have looked at the types of Naive Bayes algorithms and when to use which one. Let us go ahead and see a few examples and datasets and implement these Naive Bayes algorithms using scikit-learn. Okay. So for the first example, I'm going to import a few of the global modules that we will be requiring. So first I'm importing warning module. So I'm just going to suppress few warnings that comes up in the Jupyter kernel. Then we have NumPy and Pandas for data manipulation. Then we are going to use train, test, and split function in order to test our split our dataset into training and testing. Then we are going to use this classification report function as well. So this will generate a report or the performance matrices of the classification model that we are going to create. We are also going to use standard scaler in order to do some pre-processing on our data and scale the features. And then finally, these are the classes or the implementation of these algorithms in scikit-learns that we are going to import. First is going to be Gaussian, then Bernoulli, Multinomial, Complement, and then Categorical. I have curated a few of the datasets. So we will be providing all these codes, these datasets, and the requirements.txt file in a GitHub repository, which you can clone and practice along with us. So for this example, I'm just going to import the dataset so that we can do via pd.read CSV. Okay, and we are going to see at the dataset. So this dataset contains 4 columns. First is gender, then we have age, then we have salary, and then a final column whether they purchased iPhone or not, which is a categorical column which of value 1 and 0, which states 1 if they have bought iPhone or 0 if they haven't. Okay, so let's see a little bit about this dataset as well. So for this, we will be using this describe method, which will give us a summary of these continuous columns. Also, we will be seeing the correlation among the set of columns and whether each column is correlated with other or not. And then we are going to see whether there is empty values in the dataset or not. Okay, so this gives us the description. We see that we have 400 values for age, salary, as well as purchase. That means we do not have any null values. The mean age is 37. The mean salary is 69,000. This mean does not matter because that is a Boolean value. Standard deviation is 10 for age. Similarly, 34,000. Minimum age that we see is 18. The maximum age that we see is 60. The minimum salary is 15,000. The maximum is 1,50,000. Similarly, this gives us an idea about the quartiles of the data distribution. Okay, this gives us the correlation. So we see that there is not much correlation between age and salary because correlation. So this metric, the values in this metric ranges from -1 to 1. So -1 provides us negative correlation, that they are actually negatively correlated. So hot and warm are negatively correlated. However, rain and umbrella are highly correlated. So they will have value which is closer to 1. Okay. And 0 or anything that is near to 0, both in negative and positive side, says there is little significance or little correlation between the datasets, and these two are not actually correlated. So age and salary are not correlated, which actually matches with one of the assumption that Gaussian distribution takes. And these two are independent variables, and we do not assign any weightage to them. Also, we can see if they have null values by this value. So we can check for is NA, then sum that up in order to get whether there was any null values or not. So we say 0 null values for gender, age, salary, as well as iPhone user. Okay. So next thing, since we are using Gaussian naive Bayes algorithm, we need to know whether these particular columns that we are going to use. So in this case, we are going to use age and salary to predict whether they have purchased iPhone or not. These two are continuous columns, which is an essential for Gaussian naive Bayes algorithm, and they need to be in following Gaussian normal distribution. So from this particular cell, we are going to plot these features in their kernel density function and see with their distribution. So we can see that age is actually following normal distribution or similar to normal distribution. Salary is not that normal distribution. So you can employ some methods in order to make this normal distribution. The next thing that we are going to see is feature engineering. So in feature engineering, we actually handle missing values. We actually handle categorical values. We scale those features. We sometimes create new features or sometimes extract the features. So for this case, since we are using continuous variables which are of different scale, so you can see that age is actually in tens, whereas salary is in thousands. So once you put this into some machine learning algorithm, it will actually, the salary column will actually dominate the age value, because those are actually not in similar scale. So we need to scale them in a similar fashion so that each feature that we are going to use from the continuous variable are in the same range. So there are multiple methods of scaling. There is standard scaling, there is min max scaling, there is vector scaling as well. So for this example, we will be using min max scaler. So what min max scaler does is, for each particular set of values in a column, it figures out the minimum value and the maximum value. Then for each value in this column, it subtracts the minimum value and divides the value by the difference of maximum value from this column minus the minimum value of this column. That way it is able to put this into a 0 to 1 scale. Okay. Similarly, we will do the scaling for salaries as well, and both of these features at the end of the scaling will range from 0 to 1. In min max scaler, you can also specify the range that you want to fit that to. So there is a column called range, okay, where you can specify your own range if you want to scale that to particular range. We are going to create an object of scalar class. We are going to fit transform these columns and reassign it back. Okay. After this is done, this is how the set of values will look. They will be ranging from 0 to 1. The next thing is model creation. So for model creation, we need to segregate our features and the target variables. Features in the case which are going to be used to predict, and the target is something that we are going to predict. So in our case, we are going to use age and salary as our features, since only those two are in continuous form and follows Gaussian normal distribution, that is termed as X. So we will take out these particular columns, and then we will take out iPhone as a single series and put that to Y. Okay. This is how we segregate our features and targets. Then we are going to split this dataset into test and train dataset. That is done by this train test split function. Takes a test size. So it will say divide 70% of my data into training and 30% of my data into test. Next thing is we are going to create an object of class Gaussian Naive Bayes, which we have imported from scikit-learn.naive Bayes module. Then we are going to fit our training dataset into it, which is going to be xtrain and ytrain. And then we are going to predict that. And then we are going to predict the labels of xtest. Then after this is done, there is a method in the model itself which will tell us the score of the prediction once you give it the test input as well as the actual test output. And then we generate a classification report. So let's generate this and look into it and how this performs. Okay, the accuracy score from this model is coming around at 89%. This is the classification report that we have generated. So in order to understand the classification report, we have to first understand few of the terminologies and the matrices. So the first of them being confusion matrix. So confusion matrix is a table in which at a row level we have predicted values, and a column level we have the ground truth or the actual values that is there in the dataset. So the first thing, that is true positive, it's something that we have predicted as positive and has actually been positive. The second thing, false positive, is something that we have predicted as positive but were not actually positive. So in our case, so all those users whom we have predicted that they will buy an iPhone and they actually bought an iPhone are true positives. Our false positive are those whom we have predicted to buy an iPhone but they actually did not buy an iPhone. True negatives are those whom we have predicted that they won't buy an iPhone and I actually did not buy an iPhone. And the third one is whom we considered that they won't buy an iPhone, but they went ahead and bought an iPhone. So the accuracy of these models that we have just created is actually the sum of true positives plus the sum of true negatives divided by the entire predictions that we made. Okay. So that is the 89%. So 89% of times we have predicted something and it actually was correct. Okay. Whether it could be true positives or true negatives. That is our accuracy. So the next thing that we need to look at is recall. Recall is the number of positive that we have predicted correctly divided by the total number of actual positives. So let us understand recall by a real life example. Say that you are running a company and you want to identify all the customers who are likely to buy your product. So the higher number of recall will state that you are correctly able to identify all the customers who are willing to buy your product, and you are not missing on those customers who are willing to buy your product, but you are not actually able to flag them. So one thing to keep in mind while using recall as your metric is that it does not use as false positive as a checking metric. Okay, so what does this mean? So in case of retail or customer segmentation, it is fine that you are flagging some customer who is not likely to buy as a likely to buy customer, which will actually include some more spend from the company's side, but which is actually okay in some cases, depending on your business problem. However, if we tweak this problem a little bit, say you are now have a task of identifying all the convicts, whether they are guilty or not, and you are actually finding someone or tagging someone positive who are actually not positive, or you are giving a false positive output more. Okay, so in that case you are actually manipulating with an innocent life. Okay, so in such cases where false positive is a crucial metric to look at, or somewhere where you want to reduce your false positive number, that is where precision comes into play. So precision is the number of true positives that you predicted were actually correct divided by all the number of positives that you predicted. Okay, so how precision is used is it will keep your false positives under check or your type 1 error under check. Neither of recall or precision can identify or truly quantify the correctness of your model. It depends on the business problem. It might be that recall is a good metric for your problem to look at, whereas precision could be a good metric for someone else. So for this ambiguity and to resolve this, what we have is F1 score. F1 score is a harmonic mean of recall and precision. So this gives you a weighted idea about your recall as well as your precision. So with the understanding of confusion metrics and the different parameters or metrics that we can use to evaluate your classification score, like recall and precision and F1 score, let us move to the next classification model, which is Bernoulli's Naive Bayes. Okay, so for this again, I have one dataset. I will just import that and see its description and the initial dataset. So over here, we have these particular columns, okay, which states the age, gender, whether they have blood pressure or not, the cholesterol category, and their sodium to potassium ratio, and the drug that they used. Okay, now we need to find out for a given set of features that are assigned to us, which drug they should take. So remember, in Bernoulli's Naive Bayes, the criteria is that all your columns should be of two classes at max only. So they need to be binary or true false kind of classes for each particular feature. So we'll for now just check how many of such features are there which are of two categories. So we just see that gender and cholesterol are of two classes. Rest all of them are multi-class categories or features. So what we will do is we will do some feature engineering. Okay, so for all those categories, or so all those features which have categorical values or any values which is of not two classes, we will bin them and we will make two classes out of it. First, what we need to do is we need to classify or bucket these ages into groups. Similarly, we need to bucket Na to potassium ratio into groups as well. So for that, this is the function that I will be using. So for age, I will be creating buckets within 0 to 22, within 23 to 28, similarly till 68 and above. Similar for potassium, sodium to potassium ratio, I will create bucket from 0 to 8, 10 to 12, 13 to 15, similarly above 28 as well. So if you want to know how do we create this bucket, this is actually arbitrarily created right now. So I have created this plot where I have plotted the histogram of these ratios, the age as well as the sodium to potassium ratio. And based on the trend of this graph, I have kind of tried to identify each bucket and put them in that form. So this is a function which we'll be using to create those bucket for age, and this is another function that we'll be using to create those bucket for sodium to potassium ratio. I will just say okay. Okay, so it takes age, checks whether in which of the bucket it falls into and assign that buckets to it and gives us back. Okay. And the first line, we are checking whether there is any missing values or not, so that we can handle those as well if it is needed. So we will just run this and see how it has changed. So previously, remember, we had 23, 47, 47, 28 as our age parameters. Now they have all been bucketed into some kind of category. So we now have age 23 to 28, then 46 to 51. These are all categorical values right now. Next thing that we need to do is we need to transform this in order to make them a binary column. So we will make a column named as 23 to 28. And for each value, we will check whether this is falling within 23 to 28 and give a true false for that. So let us see how to do that. So for that, we have pandas.getDummies. What it actually does is it added this suffix after the column name and creates a binary column. So this is how it will look. Okay. So it will create a column age 0 to 22, mark 0, 0, 0, a true or false. Similarly, it will do for gender, for cholesterol, for sodium to potassium ratio, and for other columns as well. Once this is done, right now we have our data in a binary format as Bernoulli's Naive Bayes requires. All of the data, all the columns are in binary format. So before putting into Bernoulli, we need to figure out or do this feature engineering so that our data is in this format. Then we also need to label encode our final data set. Okay, so right now machine learning models do not understand strings. So we have to encode these particular classes into numbers. For that, we are going to use label encoder. There's another encoder called Ordinal encoder, which is used for feature encoding, not for the target value encoding. This is a target value that we are going to figure out. Drug is a target value. So for that, we are going to use label encoder. So we are going to create an object of label encoder, fit this entire value set of values, and then we are going to transform that and again assign to the drug column. And then we will be seeing the head of it. So once we do that, we see that drug Y is converted to 4, drug C is converted to 2, similarly drug X is converted to 3, and so on. Okay. The next thing is model creation again. It follows the same step as we did earlier. We are splitting the dataset into our features and our target labels. Then we are again splitting the entire dataset into training and test. Then we are creating an object of Bernoulli Naive Bayes Classifier, fitting the data, predicting that, getting the score, and printing the classification report. And finally, from these predictions, we are again decoding those predictions. So right now, and the prediction we will be getting numbers. So we need to decode that in order to get the actual drug name. So we will use the same encoder that we have used to encode, which is label encoder. And it has this inverse transform function, which lets you decode those. So once you run this, you will get again a similar score. You will have the score, you will have the precision, you will have the recall, as well as you have the weighted value of precision and recall, which is the F1 score. And this is the reverse mapping of the particular prediction that we got. Okay, so after this, we will move towards multinomial naive Bayes classifier. So remember, in multinomial naive Bayes classifier, it is used when the frequency of a feature is also important. Okay, so for this, I will use this particular data set where I have a movie index, okay, and the number of star rating that it got. So how many 1-star rating did it get? How many 2-star rating did it get? Similarly, so on to 5-star rating, and the type of the movie or the flag, whether it was hit, flop, or super hit. Okay. Again, we will check whether it has missing values or not. It does not have missing values. Then we will check and do the feature engineering part. Okay. So over here, all of our values are anyways in numbers. So all we need to do is we need to encode the type into labeling via label encoder. So this is where we are doing that label encoding part again. We are creating a label encoder object. We are fitting the type column over here, and then we are transforming that. Okay. So for hit, flop, and super hit, we are getting some encoded value in numeric form. Then again, we are using the same method, same kind of structure that we have followed. Again, we have splitting the features and the target values. Then we are splitting into training and testing. Then we are creating an object of multinomial naive Bayes class, training the model, getting the accuracy score, and then printing the classification report. And then finally, we are again inversing our encoded values to the actual values to see what it is. So the next classification algorithm that we need to look at is complement naive Bayes. Okay, suppose right now the data set that we have used over here, it is fairly evenly distributed again for hit, flop, and super hits. However, if we had imbalance in the dataset, the number of hit entries are really high. Say the number of hit entries are really high than that of flop entries, then we are kind of skewing the probability of getting a super hit or flop movie. Okay, how? Remember, in the formula, we are multiplying the class probability as well. So getting, if the number of flop movies in the entire dataset is actually more, so the chances of getting that will actually be higher because we are multiplying that class probability as well in our equation. So if there is imbalance in the dataset, if all your classes are not actually of equal numbers, or you do not have enough entries for all the classes, you can use complement naive Bayes method. Okay, again, this is same. We are going to use the same dataset where we have already labeled and encoded that, and we are going to put it to complement naive Bayes model, fitting them, again predicting them, and getting the predicted classification report. Okay, so over here we are getting 71% accuracy because there is actually enough balance in the dataset that we have used. However, if you have used a dataset where imbalance is there among the classes of target variable, it would have been much better than your multinomial classification. The final thing that we're going to look at right now is categorical naive Bayes. So we are going to use the same dataset that we have used in Bernoulli's and see how simplified it would be if we have used categorical naive Bayes over there. So categorical naive Bayes uses only categorical columns. So first we need to make our numerical columns or continuous columns to categories. So age is one continuous column and sodium to potassium ratio is again one continuous column. We are going to use the same logic that we used above in the Bernoulli's part and classify or bucket or bin them into categories. So after doing that, we are again having the same buckets, say age 23 to 28, 46 to 51, so on, and similarly buckets for sodium to potassium ratio. Next thing that we need to do is we need to encode these categories into numbers because machine learning algorithms do not handle string values. They only need numbers or numerical values. So for that, we are going to use an encoder called Ordinal encoder. Okay, so over here we need to pass all the variables or all the columns that needs to be encoded in the feature set. Okay, so our feature set comprises of these 5 columns. So we are going to pass all the 5 columns in the fit method. Then we are going to transform that and then we're going to see this. Okay, so this is the output from this table is output from the first set of codes, which is this one. So you are able to see that age is encoded, the categories of age is encoded, gender is also encoded, BP, cholesterol, and into potassium ratio is also encoded into numerical formats. Next thing that we need to do is we need to encode our label as well, which is drug. So we are again going to transform the labels using label encoder. And this is the set that we are going to get after that. Then similar step again proceeds. We are going to put the data into categorical features and then our target. Then we're going to split the data, use categorical naive Bayes model, fit, predict, check the score, print the classification report, and inverse transform the distinct score that we get. Okay, over here we are getting about 96% of accuracy. However, we remember over there we had to make all the columns in a binary format. Okay, so if your categorical values have more than 2 classes, then it is better to use categorical naive Bayes model than Bernoulli's naive Bayes, because otherwise you have to do this processing and make them a binary column. Whereas here you can just use those columns directly. Just after label encoding and ordinal encoding, you can directly put them to model. Okay, so with that note, this session comes to an end. To summarize, we have looked at the basic theory of naive Bayes algorithms and the probability intuition behind them. We have looked at their assumptions, the type of naive Bayes algorithms, when to use which one, and a hands-on experience on each of them. If you have liked this video, please share this with your friends and peers. Please give us your feedbacks and suggestion in the comment section below. And please subscribe to Naukri Learning for more such videos. Thank you. Good day.